Hello everyone, welcome to this short presentation on Little's Law by our group of myself, Nilesh, Dhruv and Swarali. This is a part of our group project based on uh, a group project in the course Operations Analysis at IIT Bombay. First, let us look at a overview of Little's Law. So let's look at some historical background of how Little's Law was introduced. So in 1954, a paper uh, titled, Lit- uh, titled Little's Law was proposed, and it was proposed without any proof. The form L is equal to lambda into W uh, was first published by Philip Morse, where he challenged the readers to find a situation where the relationship did not hold. This was similar to Newton's law, where simply an equation was proposed without any proof. Uh, However, in 1961, John Little came up with a proof of this law, and he showed that there is no such situation where the given condition does not exist. And Little is currently an institute professor at MIT. Little's proof was followed by a more simpler version by Joel. Shelar published a different and more intuitive proof even further in 1972. So that's how the Little law was evolved from its proposition to its proof. Now let us look at some background of Little's law. So Little's law establishes a relationship between average waiting time and average number of items waiting for a service with the average rate of arrival in a service system. It deals with queuing systems where discrete items arrive at some rate in a system, then they receive some service in the queuing system, and then they leave. So we can see this uh, through this infographic that some arrivals come into a queuing system, which consists where the items form a queue, and as they receive the service, uh, they are they leave the system. Uh, that is how the queuing system works, and Little's law tries to model such a system. Now let us look at a more formal definition of the Little's law. So Little's law is defined as L is equal to lambda into W, where L is the average number of items in the queuing system. Lambda is the average number of items arriving per unit time. W is the average waiting time in the queuing system for an item. The above equation assumes that there is a steady state reached by the queuing system. There are some more equivalent definitions of the Little's law which try to uh, establish a relationship between different quantities under steady state conditions, such as the average number in the system is equal to average arrival rate times the average time of an item in a system. Also, average number in a system is average departure rate multiplied by average time in a system. Average inventory size can also be modeled as average throughput rate multiplied by average flow time of the items. And average work in progress, WIP, can also be uh, stated as average throughput rate into average cycle time. Now let us look at the proof of Little's law with a picture. This proof was proposed by John Little uh, in his first public. So as we can see a diagram on a right, we can see a histogram like figure where in a time period T, some arrivals and some departures are happening. We can try to model this system with the following set of quantities, where small n of t is equal to the number of items in the queuing system at time t. Capital T is a long period of time in which we are considering the system. A of t represents the area under the curve of n of t over the time period capital T. Capital N of t is the number of arrivals in the time period capital T. We can see in the diagram uh, that we have shown the first departure in T and the nth arrival in T. All of these are modeled using these quantities. Then based on these quantities, we can develop some relationships and construct some more quantities like lambda of t, which is the n of t upon capital T. This represents the arrival rate during time period capital T. L of t is equal to a of t upon capital T will represent average queue length during time period capital T. W of t equal to a of t upon n of t uh, shows us the average waiting time in the system per arrival during time capital T. Now a slight manipulation with these equations give us the relationship L of t is equal to lambda t into W of t. Then at a limiting case of t tending to infinity, uh, these quantities reach a saturation point, and we can show that a relationship like L is equal to lambda into W is established, proving the Little's law. Now let us look at some applications of Little's law.
Okay. So now I'll talk about the various applications of Little's law in various domains and setups. So firstly, the we can use Little's law for the estimation of waiting times in queues, and which can be useful for restaurants and similar setups where we have to estimate the length of the queue and the waiting times. And another setup where we can use Little's law is for the planning of the ordering time of inventory and taking care of the various factors like lead time and the delivery time. And we can also use Little's law for the reduction of work in progress quantity. And we can also use Little's law in various other domains like product development. And another application of Little's law is in multitasking and assembly line kind of systems. So now I'll talk about an example of Little's law in fluid mechanics. So from the figure we can see that the arrival rate of liquid in the system is about 10 gallons per minute, and that is also the departure rate. And the work in progress inventory, that is the quantity of liquid being processed in the tank, is about 1000 gallons, and that would be the L in our little slow application, and lambda would be 10 gallons per minute. And so applying little slow, we can find out the average throughput time, that is the average processing time a gallon of liquid undergoes processing, and that would be equal to L divided by lambda, and that comes out to be 100 minutes. And next, now I'll talk about the application in communication network. So if we consider a data communication system with three routers, and packet arrives at those three routers or nodes with arrival rates like 190 packets per second, 300 packets per second, and 10 packets per second, respectively. And also, if we have calculated that the average packet, same sized packets that float in the system is 50,000, then we can use these quantities to find out the average delay per packet in the system by using Little's law, by and where the L, that is the average number of packets in the system, would be equal to 50,000 packets, and the lambda would be equal to the total arrival rate, which would be the sum of A1, A2, and A3, which comes out to be 500 packets per second. And then applying Little's law, we get the average delay per packet to be equal to L divided by lambda, which comes out to be 100 seconds. And we can use this average delay quantity to model various protocols and routing algorithms in a communication network. Now, next, I'll talk about the application of Little's law in balanced assembly line. And from the figure, we can see that assembly line which has five machines named A, B, C, D, and E, and all of them have a processing time of 3 minutes per unit, or equivalently produce production rate of 20 units per hour. So if we find out the throughput rate of the whole assembly line. That would be 20 units per hour, and the overall lead time would be 15 minutes, as it is there are 5 machines and each take 3 minutes per unit. And if we calculate the work in progress, that is the amount of units in under processing in the assembly line, using Little's law, that would be equal to the throughput into the lead time, which comes out to be 20 into 15 by 60, and we divide by 60 to convert minutes to hour, and that comes out to be 5 units. And intuitively also we can see that at a particular time each of the machine would be processing 1 unit, and hence there would be 5 units under production at a particular time. So next we'll look at some more examples.
As we have seen that the Little's law is applicable in many environments, including the communication network, manufacturing industries, and various other service industries. Let us now take a look at few examples in more detail. So this is a hospital ward example where we are trying to determine the size and the staffing level for maternity ward. From the historical records, we know that the birth rate for a local community is about 5 births per day, and on an average, a woman stays in the ward for nearly 2.5 days. Therefore, using Little's law to predict the average number of mothers in the maternity ward, we expect that the queue length is given by L is equal to lambda into W, which is equal to 12.5 mothers. However, this law has a limitation here. The law only provides the average requirements, and one would need to design the maternity ward in order to accommodate its peak requirements. For instance, if we say we would certainly want more than 12.5 mothers in order to handle the variability in the occupancy of the ward. Therefore, one needs to use queuing models or the simulation in order to explore the trade-offs between the utilization of beds. Yeah. So nevertheless, Little's law provides a starting point for this investigation since we know that the average number of beds that are needed. Moving to another example of toll booths where we want to estimate the waiting time for vehicles. Here the number of vehicles passing through an entry of the tunnel is 50,000 per day, and the expected number of vehicles waiting at any point near the target is nearly 20. Therefore, the average and the arrival rate to the toll booth is 3,600 vehicles per hour. Thus, on average, the time a vehicle spends at the toll booth is 20 divided by 3,600 hour, which is equal to 20 seconds. Moving on next is robustness and generality of the Little's law. As we know that it is used in the systems where we have steady state assumptions. However, it is nearly exact in some cases where the arrival and service processes are not so stationary. This shows that the Little's law is very robust and is general under certain circumstances. Concluding remarks, as the saying goes that the simple ideas can be extremely powerful, Little's law is one example of that. Within hands-on practice, operations, management, and computer architecture have led the way using Little's law. And such developments make the ideas easier to implement and help explain why this law has become very wide range over the past few years. And now we have come to the end of our video. We hope it was useful to all of you. Thank you.